grandson. Just telling me so. And then my daughter, who was visiting, she got a project. So there we are. So they couldn't go.
Where are we gonna put this? This is where I want it.
That's where you want it.
Because now he can see me.
Okay.
Well, so he can see this and can't see the audience. Well, he can see some of the audience, but not much. Yeah. I mean, I could turn it over this way, but.
In a crowded house, with like 7 people. That was before we went for our second.
Good morning, Nancy.
Morning, Larry.
So when I'm speaking, I really won't be able to see you. So you're going to have to interrupt, okay? You need to.
Thank you.
I can interrupt.
We have a very great business meeting here, and then we'll start the program. There'll be some ladies joining us. So first of all, let us thank the cooks for a great breakfast.
Yay.
You guys go to McDonald's
And,
and get those little things?
Burger King.
Oh, Burger King.
So this is a special occasion. This is really proud we've had in several years. We haven't even had. We had one.
Zero.
Yeah, and so it's a great turnout, and so I'm going to pass the plate. Be generous, as we use this in, for things like buying this machine here, and that brings up something else.
Larry.
If you want big contributions,
Yeah, I know.
you gotta do better than a burned out.
Oh, wait a minute, hold it, no, hold it.
By the way, don't the women have to contribute too?
Yeah.
Or they say they forgot. to
Why,
bring
you
their
don't
purse.
quit, you just keep getting in trouble.
Yeah.
Bruce has got nothing to lose.
Somebody take the show.
Oh, look at this. I think it's too late. Too late. It's already.
Nobody else.
Yeah.
Send around multiple.
Yeah, send it around, yeah.
Need more.
All right. So welcome to those who are joining us remotely. Hi, Roger. And who else is here?
Oh, you want me to get everybody up? Okay.
Yeah, sure. Why not?
All right, I can do that.
Hi.
Hi, Roger. Good to see you again. All right.
There you go.
Hey, Roger Dodger.
Hi.
This will be our last meeting of the spring, and we'll start up again in September. I'm going to pass around a sign-up sheet for breakfast. Starts in September, so here you go.
Oh, somebody's locked down.
Oh, I forgot to do that. And I forgot all about, and as we were just saying, you're too late, you've already done the dishes. Well, I wanted to touch on a couple of things. First of all, we've got these, I always want to say finer futures, that's the name of an environmental book. Faithful Futures meetings going on. And Grover Wren is on the Faithful Futures group, and he's here tuned in remote today. And he has offered to come to Yacht and Donut and kind of give us an in-depth look at what's going on. So we're going to try to do that a week from this Wednesday, subject to Grover. Are you there?
Yeah, Grover's here. Well, he was. Wait a minute. He's not now.
I'm here.
Yeah.
There he is. Okay.
Grover, I'm just saying that a week from this coming Wednesday, we'd like to have you come to Yacht and Donut. Is that going to work for you?
Yes, that'll be fine.
Okay, at 8:30 in this room. And I suppose it will be Zoom, but it's much better to come live because we have all these wonderful donuts and so forth. And so
I have to drive 45 minutes for a donut.
You should jog 45 minutes. Then you can have 2 donuts.
Oh.
No, I would die.
We'll have one in your honor.
Okay.
In memoriam.
So one more thing before we start, and that is, and this is Larry's, Larry doesn't know this is coming. But I just want to get your feel for something. You know, we have some funds, I think maybe $2,000. As I say, we bought the screen and a lot of other things, those lines. The net zero team is doing its job to try to make the church carbon neutral by the year 2000 and whatever. 35. And we have a proposal from a consultant.
After we're dead, and then they can't.
Yeah.
They're gonna blame us.
So we have a proposal from a consultant to give us some basic data and information. And that study is probably going to cost $15,000, but at this point, there's no immediate source of funding. So, and we also have to go to church council and see, in light of everything that's happening, whether this group should still be functioning, and we think it should, right?
Right.
So how do you guys feel about making investing some of our funds in the future?
How much?
Yeah.
Well, I thought- Yeah, no, no more than 1,000. What do you think?
That's
down, vote.
Well, any negatives?
well,
Yeah, sure.
that's
go ahead.
assuming the church spends the rest, I mean, we get the rest of the money from something.
Oh,
Oh,
sure.
yeah.
Yeah.
So in the meantime, what happens is it's $1,000 if we voted
It
it.
just sits where.
No, but we wouldn't have it. It would just revert.
It's already there. Right.
It'll revert back to men's
But
fellowship.
we can't spend it
No,
because we've got to hold it in case.
Oh,
this
no.
15,000.
Yeah.
We've been waiting 10 years to repave our parking lot. We are never going to get 15,000.
No.
no, it costs a lot more than 15.
No, I mean, just so,
And some of this is driven by, it ought to have been put into the budget, you know.
Yeah.
The new thing is supposed to.
Yeah.
Whatever you need for the next, into the budget.
Right.
We missed the boat for the train or whatever.
We did.
So anyway, okay, well, that's just a straw poll. I might send an email out if it gets that far. We'll just have to see.
I mean, the money has been sitting there for almost 2 years. We haven't done much of anything, but the men's fellowship money or even the green fund. I mean, we've done little things, but not a lot. And you know, our e-waste stuff, we get, how much do we get for that?
4,000 last year.
4,000.
And we are going to put 2,000 into the green fund.
Yeah, for that. Yeah, right. Okay.
Okay, without further ado, and by the way, I've miscalculated on things that I told you about, what we should talk about. Someone has pleaded, they want to know, they've come to talk about fission energy. So we need a.
Well, I will do that.
I know.
Oh, okay. All right. I hope.
All right, without further ado, I think Larry, one of these guys needs no introduction.
Okay, so Grover, you can see me, right?
Yes.
Okay, all right. So I'm going to stand here so the audience can see me. You guys just see my back or whatever. You know.
good enough.
All right, good enough. Okay, so you gotta have a title that kind of entices, motivates the audience to watch. So I tried to come up with, we're going to try to save the planet, or are we going to destroy civilization? So, okay, this last part here, I only have one chart on it, the very last chart. Okay. All of the rest is right here. Okay, so now. So I'm going to start with an apology. First of all, who in this group, you can raise your hand if you're on video. Do you know the least about physics and chemistry? Who knows the least about physics and chemistry?
Never had a class.
Can't have that many. All right, who's never had a class in high school or college, physics or chemistry? Okay, I'm going to look at you then.
Okay.
And if you look confused, or if you say, no, if you ever get confused by anything I say, you raise your hand. All right, and then we'll go over it. Or if you're so hopeless, then I'll say, how about everybody else? So, all right. So I tried to make a presentation that talked about nuclear fission without having to explain about an atom. And I can't do it. Okay, it's just, I find it impossible. There's probably other people who can, but I can't. Okay, So we're going to learn about the atom and the structure of an atom. So the hardest part is probably really the nomenclature. You know, I mean, like if you're a biologist and if I'm a biologist, I try to teach you about trees, you know, I have to say that's called a tree. If you ask me, why is it called a tree? I don't know, but it is. Okay, so nomenclature is just what we call things. Okay, all right. So here we go. An atom is composed of protons, neutrons, and electrons.
I'm with you.
Those three things. Okay, we got it. Okay, protons, neutrons, and electrons. Okay,
Never trust man, make up everything.
atoms do make up everything.
Never trust them, he said they make.
Oh, because they make up everything. That's a good one. I gotta remember that. I gotta put that right down here in a footnote. Yes. Yes, I do have the recording on. At least I'm supposed to.
Timeless.
Okay, so, all right. So a proton has a charge of +1. We call it positive. Right? A neutron, guess what? Neutron, neutral. It has a charge of 0. An electron then is a minus charge. It's negative. Okay, so if you know you got the positive and negative on the battery, that's it. Okay. A proton and neutron have about the same mass. About. Okay. But both of them are 2,000 times more massive than the electron. So a proton or neutron, teeny tiny, little. An electron is so small we can't measure it. It's for all intents and purposes, it's a point charge. Do you know what a point is? Okay. It's dimensionless. It has no dimensions, no size. That's hard to wrap around. Okay. The number of protons in an atom determines what that atom is. So every sodium atom in the world has 11 protons. Iron has 26, gold 72, uranium 92, arsenic 33, carbon 6, technetium 43. Anybody heard of technetium before? It's the most widely used radioactive nucleotide, nuclide in medicine.
How could we have missed that?
I don't know. How many people have heard of a PET scan?
Been there, done that.
Well,
We drank that stuff?
yes, you did.
Oh, my.
There you go. Okay. The charge of an atom, though, depends on the number of electrons, right? Because if you have, let's say carbon, 6 protons, 6 electrons, 6 plus minus 6 equals 0. It's neutral. If that carbon atom has now an extra electron, so it has 7, then it's -1. If it misses 4 electrons, it's +4. Okay, so that's what determines. Okay, and protons and neutrons are in the center of the atom. Okay, in an incredibly tight, small volume, and it can't be you can't take it apart unless you have a particle accelerator that goes and bombards it with something approaching the speed of light. I mean, it can't go apart, and we'll figure. And that's a really important thing with nuclear energy. If we can't take the nucleus apart, with a chemical reaction, then whatever it is, right? We can't do anything with it. And finally, electrons are spread apart in the cloud. We just call it a cloud. I'm not going to get any more technical on that. This, by the way, is really a synopsis of a 6th grade chemistry science thing. Okay, I went to the internet. Internet is wonderful, and I said, give me an elementary look. And so I'm trying to keep it at 6th grade level. I'll give you a warning when you get up to 10th grade. Okay, all right, or maybe 11th. Okay, so let's consider a carbon atom. Because we're made of carbon, right? I mean, we have a lot of carbon. Okay, so it's 6 protons, usually 6 neutrons. Okay, we call that C12. You ever hear of C13 or C14? Okay, so 99% of all the carbon atoms in the world have C12. 1% has an extra neutron, so it's C13. C14 is radioactive. Okay, that's radioactive, and we use that for carbon dating. But it's less. It is so tiny. It's like 0.00001. It's 10 to the -10th abundance compared to C12. Okay. How many electrons does a neutral carbon have? 6. Good job. Okay. So now it shows you how poorly. Let's see if I don't think my No, my laser pointer's not gonna work. Okay, well, I mean, it does, but not on the screen. Okay, so there's the nucleus. You know, if it was drawn to scale, I couldn't make a point. This very smallest pixel I could make would be like 1,000,000 times bigger than it should be. Okay, so it's really tiny. And the electron cloud, yeah, okay. I mean, it does a pretty good job because we know that the first 2 electrons go in its own orbit, if you will. That's not a bad word, but okay. And the next one goes in the next orbit, and that can hold 8 electrons, and the next one can hold 32, et cetera. So, and quantum mechanics tells us that we don't have to worry about it here. But that's just that's what a carbon atom sort of looks like. You got the protons, the nucleus in the center, really tightly packed, small, really tiny, and then the diffuse cloud of electrons. Okay, that's it. And so nuclear reactions result in a change of the nucleus. Okay, chemical reactions are those things that change the electrons. So chemistry is involved with electrons. Nuclear reactions are involved with the nucleus. That makes sense. Maybe sort of makes sense. All right. So every kind of chemical reaction in the world has no effect on the nucleus. It's just rearranging of the electrons between the atoms that are involved. That's what a chemical reaction is. You with me so far? Everybody else must be there. Okay. All right.
I'm the lowest common denominator.
Yes, you are. Okay. Nuclear reactions generate much more energy than chemical reactions. Okay. All right. So here we go. Now you sort of have the basis, sort of, but we got a little bit more to learn. But you have the basis of how nuclear energy and nuclear reactors can work. Oh, okay. The red is a warning. We just now jump from 6th grade to 10th. Okay, so here we go. All right, so why are they so energetic? Because that force that holds the nucleons, the protons and neutrons together is so strong that when it does that, it actually decreases the mass of individual parts. In other words, well, first we got to talk about this new mass. You notice that 1 AMU is what we call it, atomic mass unit. Is 10 to the minus 27 kilograms. That's really tiny and it's hard to say, bulky, everything. So we make up a new, chemists and physicists make up a new unit called the atomic mass unit. So we can speak in reasonable numbers, like 1s and 6s, 12s. Okay. All right. So a single proton has a mass of that many AMUs. Now I sort of lied to, I think, on the first chart, second chart, and I said they have about the same mass. Well, actually, that's a big difference in physics, but for us, it's about the same, right? Pretty close to 1 AMU each, right? Okay. So if you take 6 individual protons, so you take that times 6 plus that times 6, you get that many AMUs. Okay, that's what the individual parts of a C12 atom. That's the mass right there, 12 and that much. But the periodic table, the atomic masses on all the elements of the periodic table is based on the atomic mass of a C12 carbon atom, and it's defined to be 12 exactly. As an infinite number of significant figures. It's defined to be 12 exactly. So the difference is that many AMUs. What's the big deal losing that much? I mean, who cares, right? I mean, it's such a little tiny amount to begin with. Yeah. Well, there was a guy in 1905 who explained that. His first name was Albert. Okay. All right. And so that's why. Energy equals mass times the speed of light squared. Okay. Now, when you do the arithmetic and you have a little mass, that's a lot of energy, it turns out. So fundamentally, the equation states that energy and mass are the same. They're interchangeable. Okay. The equation explains why a lot of energy is released during a nuclear reaction. So let's just do that loss right there. E equals mc squared. You can do the arithmetic. I'm not going to do it. I mean, if you take the mass, right? That's the mass right there. And you multiply by 3 times 10 to the 8th meters per second squared, okay? You end up with that many kilojoules. A joule, that's 1,000 joules. So really that's 10 to the 16th joules. You say, well, I don't know what a joule is. Well, that's okay. Anybody know what okay, so I got one end of a library shelf bracketed. Let me go to the other end. Does anybody,
The end of the curve is what you mean.
does anybody know what the units of a joule are in SI notation? No, it's kilogram meter squared per second squared. Okay, that's what a Newton is. And and that's what a joule is based on. Okay, never mind. So I know we don't get that level. Okay, all right. So, but if you burn the same mass of gasoline, you get about 570 kilojoules. See the difference? In other words, 3 million times more energetic. Just by blowing apart, if you could, blowing apart a carbon nucleus and compare that to the same mass of gasoline that you burn, it's about 3 million times more energetic. Okay. So, I mean, what was it, Willie Sutton that goes to the banks because that's where the money is? If you want to make energy, you go to the nucleus because that's where the energy is. Okay, so now we're going to talk about fission and fusion. And you say, well, they're only different by 2 letters. I got an extra S here and I changed the I to a U. So is there a big difference? Well, yeah. So fission is you take one nucleus and you split it into 2 or more nucleus. Now, if you think about what we just talked about, where you take a nucleus, and you squeeze it in and you lower the mass, and then if you separate it, right, you're going to get energy out of this process, aren't you? Because you're going to get more mass. And then that mass will turn into energy, that mass difference. It's called a mass defect, okay? Fusion is you take 2 or more nuclei and you put them into one. Now, it turns out that this can happen pretty easily. It doesn't take a lot. It doesn't take much, because when you break a big nucleus and you hit it with a neutron just right, it separates it. That doesn't take a lot of stuff. This takes a huge amount of energy to get it started. Okay. Wait.
So is that what a super collider does? It collides these and fuses them? Oh, I get an A in the class?
Well, we get a B.
Oh, I'll take it.
It doesn't fuse it. But that's what you do. You take an electron, say, or even a proton. We couldn't do this for a long time, but now you can take a proton and accelerate it to really close to the speed of light, 99.99999, the speed of light, and then you ram it into something, into one thing. Now, if you can imagine how small this is, right, and think how complex your machine has to be, and how big it has to be, how powerful it has to be. Okay, I mean, it's some of the most complex stuff we've done as humans is this work. Okay, but this process takes much more energy. So we don't fuse in a cyclotron. If we could, we'd have fusion power right now. It's not that easy. Okay, but that's a B. That's a B. Okay.
The other ones go B minus.
I didn't want to say B minus because it's the first day of class, so it's okay. All right, so fission. Okay, folks, I'm pointing to this little bullet coming into this nucleus, and it's going to split it into 2. And so a lot of energy is created by that. Fusion is when you take 2 and you make 1 nucleus, and a lot of energy is involved with that. But it takes a lot. So you put a lot in, but then you get even a lot more out. And we know that that's true because we have a sun that we can look at every day.
H to HE.
A minus. Okay.
Is a hydrogen bomb fission or fusion?
Both.
Both.
Because it takes a fission bomb to create the fusion reaction, which they can then blow up.
Oh.
So you take a
blasting cap.
Nagasaki type bomb, right? And you surround you bury in it the mass needed to fuse the things you want to fuse. When that implodes, boom, right, and blows up a city by itself, Then you get a really big reaction called a thermonuclear weapon, thermonuclear reaction of fusion, and then it goes big bang. So little bang, big bang. But it takes fission to make it. Because on Earth, it turns out, you have to generate fusion. The temperature has to be at least 100 million degrees Celsius. And the only way we know how to do that is with a fission bomb. And we can't contain it, obviously. So right now, there's no way to harness it. Yes?
Fission was used in Hiroshima.
No, fission. Fission was used. Yeah,
That's what you
yes.
And fusion in Nagasaki.
No, they were both fission bombs. We didn't have fusion bombs until about 7 or 8 years after.
Okay, thank you.
Right. No, that's a very good question, though. Yeah, we didn't have a fusion bomb. How many bombs did we have when at the end of World War II? How many nuclear weapons did we have?
0.
Well, we had 3, but at the end we had 0 because we tested one in Alamogordo, right? We used one in Nagasaki, one in Hiroshima, but the emperor didn't know that, so he surrendered. Okay.
We shot our.
We had shot our complete lot because it took us 4 years to make that much uranium and plutonium enriched.
So it was the big bluff.
Well, yeah, 300,000 people killed is not necessarily a bluff, but I mean, because we could say it'll take us another couple of years, but we'll be back. Yeah, we'll be back. Okay, so let's look now. I mean, these are just kind of theoretical things. Let's look at real ones. Okay, so here is a neutron firing into a uranium-235. That neutron gets embedded. Now it has to be just the right speed. Okay, and then it gets embedded into the nucleus and becomes uranium-236, which turns out that it just doesn't like that. Okay, it's unstable. It's what we call radioactive. And so it immediately splits into 2 different atoms, barium and krypton, don't have to worry about that, and releases 3 neutrons. Now that's key. Okay, all right. But so these 2 guys are very stable. They're not radioactive. But what can these neutrons do? If you got a whole bunch of uranium-235, those 3 can hit other atoms at 235. And then I have right now I have 3 times 3 times 3, and all of those can go. And so now I have something called a chain reaction. We'll get to that later. Here's a nuclear fusion where this is a hydrogen atom with 1 neutron. This is a hydrogen atom with 2 neutrons. Deuterium and tritium. Tritium is radioactive. Okay. H3 tritium is radioactive. That was it's a very weak, it's an alpha emitter, and so you can stop it with a piece of paper. It's not, but it is radioactive. You just don't want to swallow it, you know. That's what was released in TMI, 3 Mile Island. Very low level stuff, but we went berserk. I mean, we literally, some people just went berserk. It was just the end of the world. But anyway, and so that makes this 3 neutrons, 2 protons and 3 neutrons. 1 neutron gets kicked out immediately, and that's the helium. And so this is just normal helium, the stuff that you breathe in. You talk real loud, you know, high voice. That's helium. Okay, and that's what happens in our sun. You're right, Bill. Okay, so in all stars, well, until it goes supernova, and then you make all the other elements. Okay, but anyway, so let's do energy comparison. So we already talked about this. 100 grams of gasoline will give you about 5,500 kilojoules. The energy from fusion, if you make the same amount, same kind of amount in terms of molecules, okay, that's what we call a mole. That's a unit of measure. Don't worry about it. It's just the way the chemists measure how much we got. And that mole is a measurement, a unit of amount. Okay, and so we get 1 million times more energy, even more. And fusion is 3 or 4 more times more energy than that. Okay, so you get a lot of energy, is the point, out of a nuclear reaction, if you could figure out a way to harness it. right? For a long time, all we did, the only way we harnessed it was to blow up cities. So, and that wasn't good, but harnessing a nuclear reaction, if it can do it, generates energy, right? And we figured out how to do it by the early 50s, which is not bad. I mean, it was really less than 10 years after we Alamogordo that we made a nuclear reactor. Humans can be pretty smart sometimes. Sometimes we can be incredibly ignorant and stupid, but we can also be pretty smart. Now, there's many fission reactors on the planet right now, lots. Okay, not quite as many as what we had, and we're decommissioning more per year right now than what we're building new. Okay, so here's the top 5 countries. Which country do you think generates more electricity with fission reactors? Yes. That's a B minus.
Germany.
Oh, that's
Nothing there.
China.
They quit.
Yeah, they're decommissioned.
United States.
I was gonna say United States.
Okay,
It's total.
so
percent?
total. I'm not. We got percentages over here, but so we generate 809 billion kilowatt hours. Okay, that's the measure of electricity generated. Now that's only about 20% of our electricity. France generates about, not a little bit more than a third of what we do, but that because they have a lot smaller population and everything, and they need less electricity, they generate 70%. So you were partially correct. Okay, but see, China's 5%, Russia is up close to us, South Korea is the most. If we sorted by percentage of electric needs, South Korea would be number 1. Okay, so there's lots of these things out there.
Where's Japan?
Well, after Fukushima, they're hardly at all. Okay,
That was their big.
that was their biggest one. Yeah, and but now they're really scared, just like we were after 3 Mile Island. But we didn't have a reason for 3 Mile Island. They have a reason for Fukushima. I mean, they're earthquake prone. There's no place to put a nuclear reactor in Japan that's not on top of an earthquake zone. So, I mean, that would be like putting a nuclear reactor on the San Andreas Fault. Probably not a good idea. Okay, but anyway. Okay.
Have one.
Diablo Canyon.
Diablo Canyon.
Well, you mean you talk about the one in Colorado?
No,
No.
Diablo is on the coast of California.
Oh. Well,
It's on a fault, yeah.
Yeah.
It may not be the San Andreas.
yeah, but it's not
It's
San
gonna
Andreas.
be shut down too.
Yeah. So let's talk about the chain reaction now. So here's the incident proton, the neutron that comes in, splits this atom, boom, which is the uranium, into barium and krypton, and it makes 3 neutrons that can go to 3 other atoms of uranium. And then this one will put out 3. So that's how it works, okay? And that's the chain reaction. So somehow you have to figure out, how can I control this thing so it doesn't go exponential? So the chain reaction, so I only get 1 neutron. Every time one of these split, only 1 more splits. In other words, I keep that just at 1, rather than what this is close to 3. Okay. So harnessing it is tricky. Fusion chain reaction continues, but it's prevented from accelerating beyond control. You still with me?
Yeah.
Okay, all right. So this is a little, I have to use big words here a little bit, but so effective multiplication factor, or another way to say is reproduction rate. That's another way that they talk about it. But so you have this number K, which indicates the change in total number of fission events during successive generations. And you want K to be 1. If it's less than 1, then you don't generate a stable reaction and the power drops off. Okay, so if it's in steady state and K is 1, we say that reactor is critical, which is what you want. You want a critical, steady state, stable nuclear reactor. If it's less than 1, it can't be sustained and there's no power. Okay. If it's supercritical, the reaction will grow exponentially. That's a dangerous word. Okay, if you guess that that would be bad for a reactor to be in the supercritical state, you're right. Think Chernobyl. Okay. All right. So how do we keep it so it's one? That's the trick. Of course, you know, the guys that made the atom bomb knew that before they even started, right? I mean, they knew that before they even thought about, you know, getting involved with nuclear reactors and using it for safety. All they were trying to do was, you know, win the war, right? But they knew this. They said, yeah, theoretically we could, but we're not going to worry about that right now. But as soon as the war was over, they did. Okay. Some of the same people. So the answer, you got to have control rods that absorb neutrons. So you put in materials. Okay, I'm going to use a word. You don't have it. I'll just use it. But this is a word that physicists use to show how well a material absorbs the neutrons. It has a high cross-capture ratio. Okay, that's what it's called. It's the ratio of how many neutrons hits it to how many absorb. Okay, and the higher it has that number, the better absorber is. The really good ones are like boron. It's a really good absorber, a really good control rod. We use that a lot in nuclear submarines, for example. Silver is pretty good. Ruthenium is pretty good. And so is hafnium. I don't have to worry about it, but we know that, okay? We know which ones are, because, you know, hundreds of people got their PhDs by figuring it out, you know, just what are the best control rods we can use? What's the best material? So here we go. Uh-oh. Oh, okay. I don't know why I did that, but anyway. So the reactor material. I'm turning my back to the crowd here. The reactor material are the red things. That's the radioactive material, okay? That's what is going to be releasing neutrons. But I put the control rod in that captures them. And so right now, this thing is stopped. There's no activity. But when I pull it out, now these things go crazy. And this is actually in a supercritical state. I mean, this is subcritical and this is supercritical right here. Okay, so the control rods, as you put them together so that they block the neutrons from going from one pile to the next, okay, that's how I control the nuclear reactor.
Does that affect the composition of the control rods? I mean, do they have to be replaced after a while, or there's an effective leak?
That's such a really good question. But, you know, they absorb it. And these materials can take a large number of neutrons, and there's a lot of things. So really, this thing will actually, that we design it so that the pile will become ineffective. In other words, the radioactivity level will be lower, and so now I have to replace the whole core. So the rods will outlast the pile. Okay, we just design it that way. Okay, you don't want to pull out rods and change them in a submarine. Okay, so you run the submarine until it won't run anymore, then you take out everything.
So that's nuclear waste.
When it can no longer generate electricity, yes, A+. It's nuclear waste. Yes, yeah. Okay, so let's take a look at here. So in general, a fission nuclear power plant heats water to generate steam, to turn a turbine, to generate electricity. It's sort of just like Hoover Dam works, except it doesn't generate steam, right? It just uses the water power to generate the electricity. As the turbine blades turn, they drive generators to make electricity. Then the nuclear power plants, they have to cool down somehow, so they use cooling towers where the water is up and it comes back down, or they just use an ocean. Which is why putting a nuclear power plant on an ocean is pretty good. Or a big lake like Lake Michigan, that's pretty good too. So the colder it is, the better, if you want to do that. Now, tell that to Greenpeace. Okay, so this energy, and here's the good thing about a fission reactor. It has a zero carbon footprint, zero. Okay. As long as there's a source of radioactive fuel, and for all intents and purposes, we have a pretty much infinite amount. Now, but it's not renewable. I mean, we can't go make uranium like we can make, solar power or wind, right? I mean, we don't make it, but it's there all the time, right? So we're not going to make more uranium than what we have right now. Okay, I mean, it's just not, but we got enough of it that it'll last really, really long time. And we have these other things I'm not going to talk about except right here. We have these things called breeder reactors where we can generate electricity and we can breed more nuclear fuel. That's really cool, but never mind. I'm not going to go into that. That's okay. So let's look at a typical schematic of a nuclear reactor. This is current technology. The three most common reactor types are PWRs, BWRs, and PHWRs, which are pressurized water reactor, boiling water reactor, and pressurized heavy water reactor. Okay, this is the most common, at least in the United States. And so, PWR is most common. So you can see here that, we're circulating hot water here, or, it's pressurized though, so it doesn't turn to steam. So it's like a pressure cooker. Water boils at 212 at 1 atmosphere pressure. But if this thing, the water gets up to about 250, 260 degrees. Okay, so way up. But what that does is it heats this water here coming in. See, it's separated.
So it's a controlled loop.
Yeah, but this heats up to steam. Then the steam turns a turbine, which generates electricity, which goes to your light bulb. Okay, that's a very simple. But you notice that there's pumps, and they're not perfect. There's not perfect self-containment between this and that. And so you can get, something, if this cooling pump stops, that could be some real problems, right? Maybe this reactor could get real hot, and maybe I couldn't stop it quickly enough, and part of the reactor core would melt. That's what happened at 3 Mile Island. Okay, so with me, okay?
I had to switch from decaf, but
But
I'm still here.
All right, okay. I mean, I don't expect you to go out and go home in your garage and build a nuclear reactor, but you kind of know a little bit about how it works. Okay, all right. So they keep it under pressure, so it heats, but it doesn't boil. So I explained that. I already explained all that. Okay, and if you really want to go, if you want to get, I got sources if you want to go back and get more stuff. So what's the downside? Well, right. Number one actually is safety, it turns out. Even PWRs have reliability issues, right? I mean, these pumps aren't going to work forever. And so you got to know when they're going to break down. Now you have this thing called routine maintenance that predicts, if I've got a pump that I think can last 10 years and I've got a nuclear reactor, I probably put a new one in every 5, right? I mean, just to make sense if I got the money, right? Okay. So, but nevertheless, there's still some issues. Yeah.
Not at first Plymouth.
No, right. At first Plymouth,
15 years. 15.
we would melt the core. At first Plymouth, we would melt the core. Yes. So, and these are the infamous examples. 3 Mile Island, Fukushima, which was the last one in Japan. Chernobyl was absolutely the worst, right? I mean, 3 Mile Island, they couldn't even measure the radioactivity that was released. They knew some was, but it was tritium, and it didn't even get above background. Okay, Chernobyl was noticed by the Swedes because that's the way the wind was blowing within 2 days. They said, "What the is going on?" But radioactive waste is a problem also. It has enough nuclear fuel to sustain a chain reaction for a certain number of years, just a finite number of years. Okay, at which time the reactor core is replaced. Yes.
My son-in-law's father decommissioned St. Bear from nuclear to gas. And he took me on a tour. And he showed me where they took cores out to check the radioactivity, and they showed me the place where the reactor was. Right. I said, "What do you do with all the waste?" And he pointed to a little building and there's this little building about, a half a block away. And that's where they stored it. Right. Behind a concrete wall. Well, there is no place. In fact, we tried for a long time to find big storage sites in the back of caves, I mean, Yucca Flats was one place, and they were, but the thing is that
it's actually makes more sense just to keep it where it is.
Yeah.
I mean, in the long run, we do cost-based, cost benefits analysis and the total cost of ownership. And it's just better to wait. Now, how long do you think this radioactive waste will be radioactive? Huh?
A couple hundred years.
Oh.
Oh, 1,000 years. Oh, God, I don't know.
Another order of magnitude, 10,000.
Oh, my gosh.
So remember now, the core is highly radioactive and there's no way to destroy it, right? Because remember, it's the nucleus problem, right? There's nothing we can do to blow it up. Unless we throw it in the sun. Now that would work.
Yeah.
It would. I mean, it's been proposed.
Put it on a rocket and send it to the sun?
Yes.
Yeah.
Yeah. You want to be underneath that rocket when it goes?
Nope.
No. Okay. I don't even want to be on the planet when it goes.
I don't want to be when it drops back to Earth, but yeah.
Right, exactly. Right. So there's 100,000 tons of radioactive waste in the United States right now. And around the world, there's about 250,000 tons.
Tons.
Okay, so that's what we got. Okay, so that's the downside. But, you can keep that radioactive waste and you can just hope that nobody bombs it and it's safe. If they bomb it, then we got.
We just send it all to Gary, Indiana. I mean, I don't.
We could, well, Cleveland maybe.
Cleveland.
Okay, so now we've got this thing called Generation 4 technology. Okay, and really what this is it's a group, a set of different ways to build a fission reaction, because now we thought about it for a long time since World War II, right? And so there's an international forum. And what their 4 goals is safety, sustainability, efficiency, and cost. Okay.
In that order?
No, they're all equal. Okay. Because if it costs too much, then you're not going to do it anyway. Okay. Because you have to talk to. Right. You have a nuclear reactor right now a PWR that works just fine, but I want you to buy mine. So scrap what you got and buy this one. And you say, well, can I buy it for $1.98? And I say, no, it's about 10 to the 17 more than that. And you say, I'll keep mine. I'll keep what I've got. Yes. Okay. So, all right. So the most developed generation 4 reactor is a sodium cooled fast reactor. And I'm going to show you just a schematic of that. It's sustainable and it's closed fuel cycle. So, the fuel can't intermix with the other stuff, right? I mean, it's contained and it's pretty safe. Okay. And there's some of these that are actually in operation, but there's a whole mess more, right? There's at least 5. There's 5 reactors. So there's the molten salt reactor, which has the greatest inherent safety at a higher cost. So you can see the downside there. And then we have three different versions of very high temperature reactor designs. These operate, as you might guess, high temperatures, and they permit high temperature electrolysis. You say, well, what do you mean? Well, electrolysis is to separate water into hydrogen and oxygen. So here I get 2 for 1. I get a twofer. I generate nuclear power, I generate electricity, and I get hydrogen that I can use for hydrogen fuel cells and other kinds of things. That's really cool. It comes at a cost, but maybe that cost will be mitigated by the generation of hydrogen. Okay, so all of these designs have what you may have heard of the small modular reactor, which are these things that they build in a plant. Now they're small. You can fit it on a semi. You can fit it on a trailer, move it to another location. So you build it in a factory, move it to another location, set it up, and it generates about 300 megawatts. Not a lot of power, but it would work just fine in name of a city on the west, Durango.
That would the whole city?
Yes.
Oh, more so.
Yeah, right, but it would work, plus some outline stuff, yes.
Yeah.
Okay, but none of these are yet, I mean, the best we're gonna do with these other kinds of Gen 4 reactors is they won't be ready to go commercially until 2040, 2050, something like that. Yes?
Who's doing this research on
This
this?
consortium, everybody. I mean, every first world country, you see, that's That's not the right, that's a bad word to say, first of all. Every highly developed country, every high technology country. So name one, and they're in this consortium. Okay, some of them are billionaires that are funding it because they want to make money. They want to be the first one on the market with a commercial, right? With a commercial one, it's going to take the world by storm. Okay, but most of it is done by government funds or government agencies like NSF and things like that. Okay, so here is the sodium cooled fast reactor. And I'm not going to spend a lot of time on it, but you can see that the core itself is separated from the rest of the stuff. And it uses molten salt. Okay, molten sodium. So you have to melt sodium, so it's really hot, right? But then this is cool sodium melted. So it's a difference of about 400 degrees. Okay, because the thing about it is that sodium can melt and stay at a stable temperature without boiling. So that's why you can use it. So in any event, this, and there we have 4 or 5 of these on the planet right now working. Okay. So, but now we ask the question. I'm way over.
No.
Okay. Fission nuclear reactors are not a good source of energy because of safety and radioactive waste. So what about fusion? I mean, why not, right? I mean, and the answer is they're under development. You ever go to a website under development? That's what this is, okay? And they've been under development for about 40 years, 50 years. Facts, fusion is the power source of the universe. Every star is powered by fusion. And that's it, okay? That's the power source of the universe. By the way, what percentage of the universe is hydrogen? 99%. What percentage is helium? 1%. We are less, it's the teensy tiny little bitty part of the total atoms in the universe. Most of the universe is hydrogen, an extra percent is helium, and then you got little tiny us. Okay. So they'd be much safer than a fission reactor. They couldn't go supercritical. They couldn't, I mean, they're so hard to operate. They can't do anything except stop. They either work or they don't. Okay. They have almost no emissions. I say almost because if you really want net zero, you have to take in the emissions required to build it. You know, you do that, you know, total carbon cost to build it and things. But when it's an operation, it has almost no emissions of any kind.
So, but fission is carbon neutral.
It's carbon neutral.
So it's actually, when it operates, it's actually a negative carbon because it takes into account payback for the cost of building. I mean, there's a cost of building.
No. I'm not counting. When they say it's carbon neutral.
They just talk about operating.
Yeah, they just talk about operating.
So you were kind of comparing.
Yeah, but here I really want to compare everything because this is, you know, because now that Bruce and I have been on this net zero task force, First Universalist Church in Denver, they count the carbon that it's in their building to build it. They count the gasoline that their congregation uses to come to church and go back home. They count everything. So they're trying to get everybody to go electric cars. In fact, bring your electric car to church, fully powered, and plug it in, and then we'll run off of your car. You just need enough to get back home. Yes.
Right.
Yeah.
Right. Reduce the peak.
Right. Yes. Yeah, to reduce the peak. Absolutely. It's cheaper. And so a fusion reactor would provide practically unlimited carbon-free power forever and forever. And so you say, well, man, that solves a climate crisis. Well, yeah. Okay, it does. Okay. It does.
How many? We still have transmission to worry about.
Yeah.
So how many would it take in the world of these things, do you think?
Oh, that's a good question. It would probably be one on when in the United States, we'd have 2.
Really?
Yeah.
And we can still
Yeah.
okay.
But you have to build more infrastructure to take that huge amount of energy and distribute it.
So Texas wouldn't get any energy?
We're not on the grid. I think that's a selling point right there.
I hadn't thought of that. I truly hadn't thought of that. They probably would want to be, they build their own.
Screw it up.
Is Craig breaking up with each question?
I think he is.
Oh.
Yeah.
Up to a B plus.
He's, but not only that, but he's up to like 8th grade now. Yeah, okay. All right. Let's see. What's my last bullet here? Oh, so we're great at making tools. So look at the James Webb Space Telescope. I mean, that is just incredible. I mean, it truly is. I mean, it's just absolutely remarkable. It is our pyramids. Okay. I mean, it's the 8th wonder of the world. And it's up there doing what, it's actually not quite operational yet. I'm waiting for the other shoe to drop. I'm just, but right now it looks like everything is perfect. Okay, so why can't we make a fusion reactor, for God's sake? Okay. And the reason is because it's too hot. It's too hot to handle on Earth. You say, hey, the sun can do it. Why can't we? Okay, but the sun's got something that we don't. The sun has a lot of mass, which generates a lot of something that starts with a G. Gravity. And so a fusion reaction under the intense pressure of the sun, at the core of the sun, it only takes about 10 million degrees to start a fusion reaction. You say 10 million, that seems like a lot. Well, it is, but we can handle that. We could actually handle 10 million degrees. But on our Earth, with this little tiny puny amount of gravity, which doesn't count really for fusion reactions, it takes 100 million degrees. And so there's the problem. So, and fusion reactors don't exist because we haven't tried, okay? We've spent a lot of money, okay? And a lot of people. There's currently 5 different types of reactors. I'll just give you the names in case you come across, one of these is gonna, well, your children will learn about one of these because one of them are going to eventually be commercially available, okay? But the one I'm going to talk about is the one that's furthest along right now, which is the MCF, the magnetic confinement fusion. Okay, so that's the only one we're going to discuss. JET is the Joint European Torus. So a torus, if you look at a donut, like Yum donut, you look at a donut and you evacuate the middle part, right? That's a torus. Okay, so now, but this is a lot bigger than a donut. Yeah, a lot bigger than a donut. And it is actually the test bed for this guy, the ITER. And here, everybody in the world is involved. Well, not Uganda, but every fully developed country. And oh, wait a minute. I missed a bullet. Okay, now anyway. I guess it's down here. I did talk about it. So in the core of the sun, there's huge gravitational pressures, and that allow fusion to occur at 10 million. Okay, but on Earth it has to be over 100 million. That is too hot to handle. Right, the materials just don't exist. So we get around it by devising a superheated gas or plasma that's magnetically contained, right? So we keep it, don't let it touch anything, all right? But it still radiates heat, right? So we can keep one going now for about 5 seconds if we get materials that are really insensitive to heat, okay? Can last about 5 seconds. And here we go. Okay, this is where I have it. So the jet, it's in a place called Oxfordshire, and I know I'm not pronouncing it right. It's Oxfordshire, but if I don't have the accent, but anyway, that's the city in the UK. And they've been doing this for 40 years. Okay, they've been doing this for 40 years with help. United States has helped a lot. But it's the test bed for the ITER, which is a consortium. It's in southern France. It's a consortium of the United States. The United States is probably 40% of the funding, I think. The EU, Japan, China, and used to be Russia, but I think, but since the Ukraine war, Russia, you just cross that out now. They're not, they got kicked out of that consortium for now. But anyway, this has been going on for 10 years. And what I have here, and if everything works, you can hear the sound, and so can all the audience. Grover, you put your thumb up because you're the one on my screen if you hear sound, okay? I'll introduce this just a little bit. So this is the test that took place at JET, okay? This is really a big machine. A person would be a little tiny thing right down here, okay? Okay, so this is really big, really complex, but not nearly as complex as the ITER is. Okay, all right. Now you might think that, boy, with 5 seconds, maybe we can get it to 5 minutes, and then we can get it to 50 hours, and maybe we'll have fusion next week. Well, no, this is not going to happen in time to help climate change. Climate change will already have occurred. Florida will already be underwater by time we get a commercially available fusion reactor. But this movie kind of explains this. So it does a better job than BBC is good, isn't it? And so it's almost as good as PBS, some of the PBS and National Geographic films. But anyway, this does a good job explaining the JET test.
2, 1, 0. This is the record-breaking reaction. It is more than 150 million degrees centigrade. 10 times hotter than the heart of the sun. And it happened here, the world's most powerful fusion plant, Jet Fusion, in Culham in Oxfordshire. It is, say the team here, a landmark for this technology.
These results are really significant because what we've managed to demonstrate inside Jet is that we can create a mini sun, the right kind of mini sun, hold it there for a sustained period and get really good performance levels, which is a major step forward in terms of our quest to get to fusion power plants.
Most nuclear reactors use fission. That's when big, unstable atoms like uranium are split in two, releasing lots of energy and radiation. Fusion is different. It involves forcing atoms of hydrogen together, fusing them to create helium, as well as lots of energy and just a tiny bit of short-lived radiation. Creating mini-stars inside reactors like this is one of the greatest technological challenges humanity has ever faced. Get it right, and it holds out the potential for producing almost unlimited supplies of energy pretty much forever. The key part of this reaction only lasts for 5 seconds and only generated enough power for 60 kettles, but it is an important proof of the principles of fusion. But it means there is still lots of work to do. Do you think you'll see commercial fusion in your lifetime?
Yes, I do think we will see commercial fusion.
You're confident we will?
Yes, I am confident. I want to believe in it.
So answer me this, why is it taking so long?
It is hard. It is really hard. It is very complex, but it's worth it, and we just have to do it for the future.
Fusion energy is carbon-free, but it is not going to be ready in time to get us out of the climate crisis. That shouldn't stop this research, say supporters. The enormous promise fusion holds means we've got to keep working on it. Justin Rowlatt, BBC News, Oxfordshire.
Oxfordshire.
I
You
can't.
did pretty good with that.
Yeah, I tried.
The city is called Culham Center.
Oh,
Yes, in
Okay.
Oxfordshire.
okay. So this is the last chart. This is the bad stuff. This is how we could lose the world. The biggest threat is that it becomes an existential threat to us in all life when it's used as a weapon. So 9 nations currently have nuclear warheads in their arsenal. 9. It used to just be 2. Well, there used to be just 1.
Yeah.
And then it was 2, and now it's 9.
Who's next? That's Tom Miller would ask.
Well, okay, so this is by order of total inventory. At one time, this number wasn't 12,000, it was 65,000 in the mid-80s. The total inventory in the world was 65,000, just with Russia and the United States in the mid-80s, okay? France and the UK came in about that time, but you see that they have relatively small ones. But you look at that 290, you say, boy, France doesn't have very many. But you know what? Those 290 nuclear warheads, they could destroy Russia in 15 minutes. Because France is real close to Russia. 290 could just, France alone could destroy Russia. Right now. Okay, so if you got this many, what does that say for the rest of the world? Not a lot. So, and that's all I'm going to say. I just hope that the Ukraine war doesn't break out in a global thermonuclear war. Oh, and all of these, except for Korea and India and Pakistan, are thermonuclear. They're fusion, not fission. So they're bigger bangs. Okay. So that's it. Any questions? Yes. My A student now.
I'm ready for AP physics now.
Okay. All right.
So when Florida is underwater, do they still get 2 senators? That's.
That would be a really good question. I don't know. I don't think Florida will be a state anymore.
You might get four because it'll split it in half.
Oh, maybe so. Right there.
Oh, maybe it'd be North Florida and South Florida. Oh, my God.
Or Upper Florida and
Yes.
Lower Florida.
Why is Germany deactivating its its nuclear nuclear?
Why is it doing what with it? Deactivating it?
Why is Germany?
Decommissioned there.
Decommission their nuclear reactors. Safety considerations.
Stupidity.
After Fukushima, okay.
Well, after Fukushima, yes. I mean, that was, because they have a reactor type, that's not 4th generation. Ask that question after the 4th generation nuclear reactors, one of them become, the one that's number 1, and see if Germany jumps on board there.
And now that this Ukraine thing, they're probably regretting.
They might be.
Decommissioning.
They might be, yeah. You had a question.
It was identical to that question.
Oh, was it? Okay. Why is Germany so far behind? Yes.
No, why
Why did they deactivate or decommission their reactor? Yeah. And that's it's a political decision, right?
Yeah.
Why was TMI? There was no reason to shut and close 3 Mile Island. There was nothing. It was such a little, but
I thought Merkel was smarter than that.
well, she probably is, but she's leaving and
She's gone.
she's gone now, isn't she? Yeah.
So-
She's actually a chemist.
I know.
She's a physical chemist.
Yeah,
Yeah, so she knows this better than I do. Yeah.
I doubt that.
Well,
A plus. I have a comment.
yes,
I have a comment. You keep saying too hot to handle.
yes.
And you might like to know that there's already been a symphony written about this.
Oh,
And it's performed here in Denver around Christmas time. That's a Messiah takeoff. And Ken, you can talk about it a minute or just tell us what it is.
Yeah, Marin Alsop with some jazz people. If you go to hear it, Too Hot to Handle.
Handle.
Oh, but it's an incredible Messiah.
okay.
I've heard it 4 times and just thinking about it, my hair stands on
Stands up,
end. It's just
okay.
so- Yeah,
Okay.
They still do it? I mean, she's gone.
yeah.
Yeah, it's coming back.
Are there any questions? Let me see here. Let me stop the share. And let me take a look at everybody. Are there any questions out there? Oh, there's Susie and there's Tammy and Bob
Hi, Bob. Bob Redwine. Good to see you.
and Jack. Any questions out there or just any comments?
Larry, I've read reports in the general media of efforts underway at a couple of universities and Lockheed Martin and a few others to develop small package fusion reactors, and which gave the impression that there was the potential for earlier commercial deployment than we're talking about this morning for the giant fusion reactors.
We'll just have to wait and see, Grover. I am skeptical. I don't know how you could. I'm not as skeptical of that as I am of cold fusion, but I just don't. I mean, it's a wonderful dream, but I don't think you can get fusion on Earth without having a huge amount of heat. Jack, you had a comment? Now, Grover, you're not talking about the small modular fission reactors, right? You're talking about fusion.
Fusion.
Yeah, okay. Jack, I thought you don't have a question? No, okay.
Oh, there, about 30 or 40 years ago in Utah, some people were cold fusion.
Oh,
That was
yes.
a big issue.
Fleischmann, yes.
Yeah.
Yeah. That's okay. So that's how science works. Science to be a science. It's been always held ever since philosophers thought about it. It had to be falsifiable. Right. So in other words, repeatable. Right. And if it's not repeatable, then it's not true. But now we're at the stage of science where you can't test the theory because it requires too much energy. So there's this thing called string theory, which gets around the problem of the just so universe that we live in. And that's a whole nother talk. But, if the mass of the electron was just a tiny bit off, or the particle that holds the protons and neutrons together in a nucleus was just a little bit more stronger or a little bit weaker, our universe would be completely different, probably couldn't support life. Okay, so we live in a just so universe. But if you have a billion universes, or a trillion, or an infinite number of universes, then, sooner or later, one of them is going to have the right physical properties to support life. And so that's what the string theory does. And it's mathematically, it's sound. The arithmetic works out, except it's not really arithmetic. I mean, this is really complicated math, but it works out that the multiverse could be there in reasons for it. And it also explains or helps explain dark matter and dark energy, which is also postulated now to get around the one problem that the standard model has, that the universe is accelerating too quickly. So, but anyway, that's way beyond what this is here. But yeah. I mean, this is graduate school stuff now we're talking about. But it's interesting. I like to follow it, see where we're going. But so a lot of people, including me, don't count string theory as science. Okay, and as Karl Popper said, it's not science. It's not even wrong. Okay, go ahead.
Doug had a question.
Yeah.
If folks have access to HBO or maybe in some other way, it's a long series. They did a show on Chernobyl.
Oh, yeah.
And it's I found it to be, well, horrifying.
It's scary.
But very informative. Right. Because one of the things that it presents is that the safety factors of nuclear fission are one thing. The people issues in terms of people and governmental issues that surrounded that whole thing are really fascinating.
And it was repeated with Fukushima because the Japanese culture, the engineers in the nuclear power plant didn't want to lose space, essentially. And so it caused all kinds of problems in the first weeks, just like Chernobyl did, but that was for purely top governmental political reasons, right? Yeah. So they're going to do another movie. Somebody will do a movie about Fukushima and tease that apart about why that was such a problem. But in fact, I got a classified briefing on that in the Pentagon about people that looked at it in the Joint Staff and said, "What? Why did they do that?" And it was all came down to culture.
Reluctance to tell the truth.
Right.
According to truth.
Well, yes. I mean,
What was
too much quibbling. Yeah.
Well, then there was the bureaucracy.
Then the bureaucracy
But
behind it.
the fundamental problem is getting an answer to the question. You got to know what the questions are.
Exactly.
What the facts are on the ground, and you couldn't get that out.
Right. Yes.
I think that Jan wanted.
Oh, Jan has a question first.
People are never the problem. It's the way the universe is made is the problem.
Oh, yes. Right.
Not me, guilty.
Jan, I'll just have a comment to that. Okay, there are people in the world who believe that the universe actually gives a crap about us. There are. I mean, I'm serious. They think that you know, because I got up in a big conference of these relativists or whatever, and it just drove me crazy. My head was exploding. And so I stood up and I said, look, do you think that if the earth goes away tomorrow and every human is gone, do you think the rest of the universe is even going to notice that force will no longer equal mass times acceleration? And she said, yes. So anyway, so go ahead, sorry.
Because cultural change takes so much time, is there any evidence that selling hope or selling the potential here, the safe potential, is there any evidence that it is starting? It's easy to sell fear. There's a lot of profit in fear. We're still, all you have to do is mention 3 Mile and Island, and then you've ended the conversation.
Right, yeah.
Is there any evidence that there's any effort to begin to give a 6th grade education even to the population? There's thought of that. I belong to the American Society for Engineering Education. And there's a group that talks about just that. And there's another group in the International Council of System Engineering. No, we're trying to push that into all the curriculum of all the colleges. We'd like to do it in the high school, but that's just so. Isn't that CRT though?
Oh, well, yeah, it might be. I mean, but we're trying. I mean, we're making the attempt, and we have made some, at least in COSI, the International Council of System Engineering, we have made some inroads in a couple of universities to try to get systems thinking, which is the only way to really solve any complex problem. It's at the system level. But it's slow work. I mean, I've been working on this in COSI, see, the first time, 2007. So it's been a while.
I think we'll take 2 more questions,
No, I just want
and then we'll conclude.
I just want to feed in. It seems like what you discussed, very technical. When we look at all the world today, where we can go to Mars and land and come back and all this stuff, but we still have not been able to get anywhere close to personal relations between people.
No, right. I mean, that's
You got, even within our religious community,
Right.
you got the evangelical
Right.
and whatever else.
and Jan is right. Fear is a primitive, primal emotion, right? That everybody has. Hope can be beaten out of you, right? I mean, I think it's so.
What you talked about was the face saving entertainment.
Yes, yeah.
That's what we're facing.
Right, exactly. Okay.
So Tom put it, I want to remember everybody, excuse me, everybody remember Tom.
Yeah, hi, Tom.
We don't see him around here as much as we'd like to, but anyway. go
I was
ahead.
going to comment on the motivation of hope and fear. And
Yes.
And thinking of the politicians, which play a pretty critical role in any ultimate solution.
Right.
I'm looking for the politician that says, I hope one day you don't need me.
Right. Right.
But I don't think you're going to find that.
Probably not. No.
So I think education is important. And I think, this summary today was very helpful to me. And I happen to have a fairly significant amount of scientific knowledge, but if we could even get this level of knowledge spread across the world, I think we can start to mitigate the power of fear that I think is holding everything back.
Yeah.
But that politicians thrive.
Right. I mean, that's how they get elected.
We'd like to thank Craig.
Yeah, let us thank Larry for yet another fabulous technical. And I also want to say one thing. I've heard Larry do this in another group, and he went down below the subatomic particle for many orders of magnitude. So you're lucky.
Oh, we're stupid.
See, I did not say that, I didn't actually even mention, I don't believe, that protons and neutrons are made in smaller particles.
Right.
So that's okay.
Well, you promised me at Yacht and Donut, you wouldn't go deeper than proton.
I did.
That's why I'm sitting here, yeah.
That's it. That's why I did this. Yes.
All right, but kind of a follow-up question. Would you favor legislators being scientists versus attorneys and lawyers?
Let me go. Yeah, I would, but not some of them should be scientists and engineers, but what they need to be mostly are commissioned officers. If they've not been in the military, in fact, I would say change the citizenship laws. Join the military or you're not a citizen.
Well, there's the start to another.
Israel.
What are you doing at this church?
And on that note.
All right, so let's everybody stand where they are and we'll do our
Oh.
traditional closing with the Lord's Prayer.
Let me close this. Thanks, Larry.
Join us at home if you'd like, please.
Wait.
All right. Our Creator in heaven, hallowed be your name. Your kingdom come, your will be done